Alright, we are going to run through a quick tutorial on how to engineer a general diaphragm design for a flexible diaphragm. I've gone ahead and drawn a very simple building since that's what we always see when in design. We have a 150 foot by 50 foot rectangular building with one interior shear wall and exterior shear walls. Here is the elevation. I apologize for the lighting and the handwriting. We'll work on the lighting. Not sure the handwriting is going to improve. We have a wind pressure on the side of our building, 5-foot parapet, 20 feet tall. So we're going to go ahead and figure a line load uniformly distributed on the roof diaphragm here. So we go ahead and take our 20 pounds per square foot wind load times our tributary area, and we get .300 pounds per linear foot. We then want to go ahead and figure what our shear is going to be at our shear walls. Start with our interior shear wall. What we want to do here, or what we can do, is put a drag strut. So this roof joist would have an axial load that would need to be designed for. We don't have to put the drag strut there, but then we would only have this distance of shear wall, which we would need to transfer the shear, and you can get some pretty high shear forces there without putting in the drag strut. So our total shear here, we will assume a simple span beam for our flexible diaphragm. So this is the deflection of our two simple span beams. So we're just going to go ahead and take 300 pounds per linear foot times a tributary area of 75 feet. We get 22.5 kips. So a decent amount of shear there. With the drag strut then, we would have 22.5 kips divided by our 50 feet. And we would have 450 pounds per linear foot. Decent amount of shear in your diaphragm. However, let's say this was only 25 feet. Without the drag, we would have, or the drag strut, or sometimes called the collector, we would only have 25 foot in which we would need to transfer that. So basically half, we would get double the shear. And that is a lot for a diaphragm. So you're better off putting in a drag strut and collector. You might be better off. The axial force in your drag strut is going to be equal to that 25 feet times your 450 pounds per linear foot, which is going to be 11.25 kips. You're also going to have to detail up the connection here to your shear wall to be able to transfer that into the shear wall. Next, we want to take a look at the cord design, or the top and bottom flanges. This up here will be in compression, this will be in tension for this direction of loading, just as a beam would be. So we're going to take our WL squared over 8, simple span beam, 450 pounds per linear foot times 75 squared divided by 8, and this will give us .316.4 kip feet. Now, to get the tension and compression, we will go ahead and assume a TC couple, not a TC couple, but like a truss action, where we have our compression cord up top, tension cord below, this is our depth of our beam. So here's our depth of our beam, compression, tension. So M divided by your D, 50 feet. Give us 6.33 kips. So this 6.33 kips is what you will need to design your chord forces for, which could be top chords or top plates, double top plates of a stud wall, or it could be your deck angle if you have a steel deck, but that would need to be detailed. Next we'll discuss real quick the general deflection criteria and analysis of a deck. Later we'll go into each specific material